Welcome to the second part of this triple series on electrical transmission. By now you would have known a lot about how electrical energy is generated and transmitted via transmission lines. If not, you can check our previous series. Today we will continue with analyzing power transmission lines using mathematical equations. In the previous series, we know that transmission line performance depends upon three parameters, which are resistance, inductance, and capacitance. These three parameters are distributed uniformly along the whole length of the line. Resistance and inductance form the series impedance, while capacitance exists between the line conductor and the earth conductor. However, because we were analyzing short transmission line in the previous series, and also because the effective length of the line is less than 100 kilometers, capacitance was neglected and assumed to be zero during our calculations.
So, unlike short transmission lines, which has an effective length which is less than 80 kilometers and with a voltage rating that is less than 69 kV. Medium transmission lines, on the other hand, is a line that has an effective length of between 80 kilometers to 150 kilometers and with a line voltage that is as high as between 69 kV to 100 kV. Lines with that parameters is usually considered as a medium transmission line, which is due to the sufficient length and the voltage of the line. So unlike short transmission lines, the effect of capacitance is taken into account while studying the medium transmission line performance. That said, although the capacitance of the line is usually uniformly distributed over the entire length of the line, but yet, reasonable accuracy is obtained by considering the capacitance of such a line lumped at one or more places. The method of lumping the capacitance at one or more places is known as localizing of line capacitance, and it gives fairly accurate results. That said, the various methods employed in localizing medium transmission line capacitance are condenser method, nominal T method, nominal pi method.
In condenser method, the line capacitance is lumped or concentrated near the load or at the receiving end. However, just that, this method overestimates the effect of capacitance. But for knowledge's sake, we will go ahead and analyze the circuit, and as a result of that, we have this circuit here. Here is the sending end voltage, which is in series with this resistance here, and further in series with the inductance there, while the condenser is in parallel there, and the load is terminated at the end of the circuit there. Also, the receiving end voltage is denoted here. That said, from the sending end, the current will flow through the resistance and the inductance. However, at the node here, the current will split into two, and in such a way that the current will flow to the condenser and the load respectively. The current flowing to the condenser will be denoted IC, and the current flowing to the load will be denoted IR.
With that circuit diagram there, we can easily derive a phasor diagram from it. Now, we will make the receiving voltage here as the reference vector, and because virtually most of all the connected load in transmission lines are inductive by nature, hence the receiving current will lag behind the voltage by 90 degrees, while the current flowing through the capacitor will be leading the voltage by 90 degrees. Also, we can shift this here. So when we apply Kirchhoff's current law here, which states that the algebraic sum of all the currents entering and exiting a node must equal 0. With this in mind, we can use it to work out how our circuit equation will be. That said, the resultant of the receiving end current IR and the current flowing through the capacitor IC will equal to the sending end current IS. Overall, in order to get the sending end voltage, we will need to analyze the resistance and the inductance. So the current flowing through the resistor will be joined here, and the current flowing through the inductance will be joined there. So the resultant of the receiving end voltage and the current flowing through the resistor and the inductance will equal to the sending end voltage. Overall, the angle between the sending end voltage and the sending end current will be the sending end power factor, while the angle between the receiving end voltage and the receiving end current will be the receiving end power factor.
Now with that circuit and phasor diagram there, we can easily use it to solve this medium transmission line problem here. For example, a medium single-phase transmission line with a length of 135 kilometers long has the following constants. Resistance per kilometer is 0.26 ohms, reactance per kilometer is 0.8 ohms, and susceptance per kilometer is 14 times 10 raised to power minus 6 Siemens. The receiving end line voltage is 132 kV, and the line is delivering 3000 kilowatts power at a power factor of 0.8 lagging. Now, assuming that the total capacitance of the line is localized at the receiving end alone, determine the sending end current, the sending end voltage, the line regulations, and the supply power factor.
Those constants here can easily be calculated. And before we can start calculating them, let's convert the value of cost to sine, which is 0.6. Using the phasor diagram here to solve the line problem. We can now start applying Kirchhoff's current law to the circuit. So looking at the first problem, which is to calculate the sending end current, IS will now equal to IR plus IC. Now before we will proceed, there is a need to get the value of IR, which is equal to the ratio of power delivered over the receiving end voltage multiplied by the angle of current to voltage at the receiving end. That is 30,000 times 10 raised to power 3 all over 132,000 times 0.8. The resultants of these numbers here will equal to 284.09 amperes.
It's fine that we have gotten the current received at the receiving end. However, in order to be able to add the value gotten with IC, which is the value of the capacitance, then there is a need to convert the current gotten to vector form. That is 284.09 multiplied by 0.8 minus j.6, which is the imaginary number. So IR will be 227.27 j170.45. Similarly, the value IC can also be calculated separately too. So IC will equal to the receiving end voltage over the imaginary of XC. So when we multiply 14 times 10 raised to power minus 6 multiplied by 135, this will equal to 18.9 times 10 raised to power minus 4. So we will multiply it by 132 kV. With this, IC will equal to J249.48. Now that the value of IR and IC has been calculated and gotten separately, the sending end current will now be the summation of the IR and IC. The resultants of these numbers will equal to 227.27 minus J79.03. Now when we convert our answer here, that is from triangle to polar form, IS will be 240.62 amps at an angle of minus 19.17 degrees.
So at the sending end, the current lags behind the voltage at an angle of minus 19.17 degrees. Again, in order to solve the sending end voltage, we will have to look at the phasor diagram again. So we will consider the receiving end voltage and the impedance that restricts the flow of current within the circuit. So looking at how far we have come, most of the constants or data that we need are already available. So the sending end voltage is equal to the receiving end voltage, which is 132K, plus the sending end current, which is 227.27 minus J79.3 multiplied by the impedances. In our case here, we will have to consider the line impedance. The real is 35, while the imaginary is J108. Again, in order to be able to multiply both, there is a need to convert them from triangle to polar form. After conversion, we can now multiply the real part of both the sending end current and the impedance together, while the imaginary part of both will be added together. However, in order to be able to add the resultants of these two, then there is a need to convert our answer to triangle form. Now the sending end voltage is 148.488.14 plus J21777.52 volts. While for us to be able to get the angle between the voltage and current, then there is a need to convert back to polar form. That is 150.07660 volts at angle 8.34 degrees.
Just like you said the other time, 8.34 degrees is the angle between current and voltage at the receiving end. Also, now that we have known the value of receiving end voltage Vs, the regulation of the line can also be gotten as a result, because we already have most of the parameters at our disposal. So the sending end voltage minus the receiving end voltage all over the receiving end voltage multiplied by 100%. The resultant of these numbers will equal to 13.69%.
Finally, in calculating the supply power factor, we will have to consider the angle between the sending end voltage and the sending end current. So adding 19.17 plus 8.34 will equal to 27.51, and the cos angle of 27.51 will equal to 0.88 lagging. So the supply power factor of the line is 0.88 lagging.
So that's pretty much of it on end condenser method. Although it can be said that this method is very simple to operate and analyze, but there are some limitations that come with this method. End condenser method assumes that the capacitance is to be lumped near the receiving end, which is because of the way the capacitor is analyzed in the circuit. But, in the real sense, capacitance is distributed along the transmission line length. Due to this, there is a considerable error of about 10% in the calculations. So the effects of the line capacitance are overestimated using this method. That is it for the first part, this twin series on medium transmission lines. In the second part, we will be analyzing a medium transmission line using nominal T method. So until then, peace.